Now in this lecture I'll answer two questions. In the first question we find out the radius of this circle that blocks quadrilateral ABCD. And in the second question we find out the length of this line segment AP is equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have quadrilateral ABCD that is inscribed by this circle. In addition, we know that AC, called AC, is the diameter of this circle. We also know that AB equals to BC in its length. We know that the perimeter of this quadrilateral ABCD is equal to 18. That is to say, the sum of its four sides lengths in total is equal to 18. AB plus BC plus CD plus DA equals to 18. In addition, we know that the area of this quadrilateral ABCD is equal to 16 square units inside. Again, our test is to find out the radius of this circle. So, we start. First of all, we define the lengths of the side lengths of quadrilateral ABCD with names. We define the length of side AB as A. AB equals to BC, and therefore BC must be also equal to ABC in its length. We define the length of side AD as B, and we define the length of side CD as C. So here we can implement all 7 in our drawing. Repeat quickly, all 7. According to all 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle, and therefore according to this rule of 7, peripheral angle ACB must be equal to 90 degrees in its size. So according to rule 7, any peripheral angle that subtends on the diameter of this circle must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. In our drawing, this is peripheral angle ABC that subtends on chord AC, that is the diameter of the circle according to what is given as the question. And therefore, according to rule 7, peripheral angle ABC must be equal to 90 degrees in its size. Likewise, this is peripheral angle ADC that also subtends on chord AC, that is the diameter of the circle, and therefore must be equal to 90 degrees in its size according to the same rule of 7. So in the next step, we'll implement the Pythagoras theorem on those both right angles. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So in the right angle ABC, here by PT is a relation for Pythagoras theorem. So in the right angle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, according to the Pythagoras theorem, in the right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so we have to substitute it is AC squared equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, we should find out that AC squared equals to A squared plus A squared, that is 2A squared. AC squared equals to 2A squared. This is according to equation 1. In the next step, we represent the Pythagoras theorem on this right triangle, triangle ADC. According to the Pythagoras theorem, in the right triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. And again, according to the Pythagoras theorem, in the right triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. AC is the missing side, so it is AC squared equals to AD squared. AD is B, therefore AD squared is B squared plus DC squared. DC is C, therefore DC squared is C squared. So in total, we found out that according to equation 2, AC squared equals to B squared plus C squared. So we have two equations for AC squared. According to equation 1, AC squared equals to 2A squared, while according to equation 2, AC squared equals to B squared plus C squared. So in the next step, we get equation 3 that states that AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2 is equals to B squared plus C squared. So in total, we should find out that 2A squared equals to B squared plus C squared. Here we divide this equation 3 by 2, and finally get that according to equation 3, B squared plus C squared over 2 equals to A squared. It is given us the question that the perimeter of this quadrangle ABCD In total it equals to 18 units. That is to say AB plus BC plus CD plus DA equals to 18. AB is A, BC is also A, CD is C, and DA is B. So in total, we get that AB plus BC is A plus A, that is 2A, plus CD, that is C, plus AD, that is B. So in total, 2A plus C plus B equals to 18. And again, the sum of the four sides terms of polynomial ABCD equals to 18. That is to say, 2A plus B plus C equals to 18. That is according to equation 4. It's given us the question that the area of this polynomial ABCD equals to 16 square units in its size. Polynomial ABCD consists of those two shapes. For right angle, the first shape is right angle ABC, this is the second shape, this is right angle ADC. It is very clear that the polynomial ABCD must be equal to the sum of the areas of those two shapes that it consists of. So, the polynomial ABCD must be equal to the area of the first shape that is consisted of, the area of this right angle ABC, plus the area of this second shape that it consists of, the area of this right angle ADC. And again, the area of polynomial ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, the area of right angle ABC, plus the area of the second shape, the area of right angle ADC. It is given as the question that the area of polynomial ABCD equals to 16 square units in its size. So we substitute the area of polynomial ABCD by 16, and it is equal to the area of this right angle ABC. What is the area of this right angle ABC? The area of right angle ABC it is equal to the base AB times the BC over 2. AB is A, BC is also A over 2. So in total it is 8 times A over 2, that is A square over 2. So in total we should find the area of the right angle ABC is equal to A square over 2 plus the area of this right angle ADC. What is the area of this right angle ADC? The area of right angle ADC equals to the base AD times the IDC over 2. AD is B, DC is C, divided by 2. So in total it is equals to B times C over 2. The area of the second shape, that is the area of the right angle ADC equals to B times C over 2 square units in its size. So in total we found out that 16 equals to A square over 2 plus BC over 2. So here we multiply this equation 5 by 2. And finally we get that according to equation 5, 16 times 2 is 32 equals to A square over 2 times 2 is A square plus BC over 2 times 2 is BC. So in total, according to equation 5, we actually found out that (32) equals to A square plus BC. According to equation 3, we found out that A square equals to B square plus C square, B square plus C square over 2. According to equation 3, A square equals to b squared plus c squared over 2. And again, according to equation 3, we only found out that a squared equals to b squared plus c squared over 2. So I can substitute a squared in this equation 5 by b squared plus c squared over 2 from this equation 3. We'll do it now, and again that according to equation 5, 32 equals to a squared according to equation 3 is b squared plus c squared over 2 plus bc. So in total, according to equation 5, we actually found out that 32 equals to b squared plus c squared over 2 plus bc. So here we multiply bc by 2 and then divide it by 2 in order to overcome the factor of this expression. And we get that 32 equals to, we have b squared plus c squared over 2. And we have to multiply bc by 2, so it is 2 times bc. Then we divide it by 2, so we change nothing. So in total, we found out that 32 equals to b squared plus c squared plus 2 times b times c over 2. Here we multiply this equation 5 by 2, and find again that according to equation 5, 32 times 2 is 64 equals to b squared plus c squared plus 2 times b times c. Here we use the algebraic identity that states that a squared plus b squared plus 2 times a times b equals to a plus b squared. So, according to this algebraic identity, we get that b squared plus c squared plus 2 times bc equals to b plus c squared. On the other side of the equation 5, we have 64. So in total, we should found out that 64 equals to b plus c squared. Here we take out of this equation and finally get that according to equation 5, b plus c equals to the square root of 64 is 8. This is according to equation 5. According to equation 5, or according to equation 4, we only found out that 2a plus b plus c equals to 18. According to equation 4, we only found out that a plus b plus c equals to 18. So now we can substitute b plus c in this equation 4 by 8 from this equation 5. So bc equals to, again we substitute b plus c in this equation 4 by 8 from this equation 5 because b plus c equals to 8. We do it now, we get that according to equation 4, 2a plus b plus c, and b plus c equals to 8 according to equation 5. 8, so 2a plus 8 equals to 18. So here is we subtract 8 from this equation 4, and finally get that according to equation 4, 2a equals to 18 plus 8 is 10, so 2a equals to 10. Here we divide this equation 4 by 2, and finally we get that a equals to 10 over 2, that is 5. And again, I should found out that a equals to 5 units in its length. So this is side B8 is equals to a, and a equals to 5, and therefore AB also equals to 5. Likewise, side BC is equals to a equals to 5, and therefore BC also equals to 5. So in the next step, we implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in this triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, in the right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. BC is also 5, therefore BC squared is 5 squared, that is 25. So in total, we found out that AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we substitute 50 by 25 times 2 and get that AC squared equals to 25 times 2. So here we take out all those equations and finally get that AC equals to the square root of 25 is 5, and so inside root we left only with 2. AC equals to 5 times root of 2 units in its length. AC is the hypotenuse of this triangle ABC, but AC is also the diameter of this circle. Note that the radius of a circle is equal to the diameter over 2. So we define the radius of this circle as R, that is the radius that we are looking for in this question. So the radius R equals to the diameter AC over 2. AC is 5 times root of 2. So if we divide the diameter by 2, we get the radius. So in total, we found out that the radius R of the circle, that is the radius that we are looking for. In total, it is equal to either 5 times root of 2 over 2 units in its length. In terms of numbers, it is equal to 3.5 0.36 units in its length. And that is the answer to the first question. Read again. I should find out that the radius of this circle, it is the radius that we are looking for, the radius R, equals to either 5 times root of 2 over 2 units in its length. On the first of numbers, the radius of this circle R equals to 3.536 units in its length. We'll finish with the first question. In the next step, I will present you the second question and we'll solve the second question of this lecture. In the second question, our task is to find out the length of this line segment AP, and this equals to x. We have to find out the value of x. So, in the drawing, we have a circle that is inscribed by this right angle ABC. This is a right angle. Angle ABC is a right angle. In addition, we know that from point S we have a tangent that is tangent to this circle at this point. So we define the point of tendency of this tangent in this circle as M. Again, SM is a tangent to the circle, point M. In addition, we know that line segment QS equals to 25 units in its length. This is called PO, that equals to 24 units in its length. Again, our task is to find out the length of this line segment AP, this equals to x. We have to find out the value of x. So first of all, we can implement rule 2 in our drawing. I'll repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle. This is the common external point, point P. For this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule 2, the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because if we focus on this common external point, point A, on this common external point, point A, we have two tangents to this circle, tangent AQ and tangent AP. According to rule 2, they are equal to each other. That is to say, AP equals to AQ, but AP is x, therefore AQ must be also equal to x units in its length. We define the length of this tangent BM as A. If we focus on this common external point B, on this common external point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ, but BM is A, therefore BQ must be also equal to A units in its length, according to rule 2. In the next step, we'll focus on this common external point, point S. For this common external point S, we have tangent SM, that is tangent to this circle at point M. Likewise, we have here chord PQ. If we extend chord PQ touches point S. Again, the extended chord PQ touches point S. So actually, all the requirements of rule 10 are satisfied, and therefore I can implement here rule 10. So I'm going to click on rule 10 according to rule 10. First of all, rule 10 is true in any circle. So in any circle, if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true. PT square equals to PA times PB. Again, PT square equals to PA times PB. In the moment we have a circle, this is tangent PT, it is tangent to this circle, point T. Likewise, we have the extended chord BA touches point P. So in this moment, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So as I mentioned before, all the requirements of rule 10 are satisfied if we propose the current sum point S. On the current sum point S, we have tangent SM, that is tangent to this circle at point M. Likewise, we have chord PQ. The extended chord PQ touches point S. Again, all the requirements of rule 10 are satisfied, and therefore can implement a rule 10. According to rule 10, SM square equals to SQ times SP. Again, SM square equals to SM square equals to SQ times SP. So write it down. According to rule 10, SM square equals to SQ times SP. Again, if we focus on the current sum point 10, if we focus on the current sum point S, according to rule 10, the following equation is true. That SM square equals to SQ times SP. SM is the missing tangent, so it is SM square equals to SQ times SP. SQ is 25 times SP. What is the length of SP? SP in total equals to SQ, that is 25, plus QP, that is 24. So in total, SP equals to 25 plus 24, that is 49. And again, in total, if we found out that SM square equals to SQ, that is 25, times SP, that is 49. So here we'll take a root out of this equation. And finally, we get that SM equals to the square root of 25 is 5 times the square root of 49 is 7. So in total, SM equals to 5 times 7, that is 45. The length of tangent SM is 35 units. This is tangent SM, equals to 45 units in its length. what is the length of this missing line segment? Line segment SB. SB in total equals to SM minus PM. So it is on SB, let me say line segment SB in total is equal to SM minus PM. So SB in total equals to SM, that is 35, minus BM, that is A. So total SB equals to 35 minus units in its length. In the next step, we will implement the Pythagoras theorem on this green right triangle QBS. So this green right triangle QBS, according to the Pythagoras theorem, QS squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. Okay, again, in this right green triangle QSB, according to the Pythagoras theorem, QS squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. QS is 25, therefore QS squared is 25 squared, that is 625. And it equals to QB squared. QB is A, therefore QB squared is A squared. Plus SB squared. SB is 35 minus A, therefore SB squared is 35 minus A squared. So in total, we should find out that 625 equals to A squared plus 35 minus A squared. So 625 equals to A squared plus 35 minus A squared. 35 minus A squared equals to 35 squared, that is 1225, plus A squared, minus 2 times 35 times 8, that is minus 78. So 625 equals to A squared plus A squared is 2A squared. We have minus 78 plus 1225. So here we subtract 625 from this equation. After we subtract 625, this side of the equation we left with nothing, this is to say 0. While on the other side of the equation we have 2A squared minus 78 and 1225 minus 625 is 600. So total, if you want to know the 2A squared minus 78 plus 600 equals to 0. Here we divide this equation by 2. And finally we get that 2A squared over 2 is A squared. Minus 78 over 2 is minus 35A. We have 600 over 2 is 300. 0 over 2 is 0. So in total, we should find out that A squared minus 35A plus 300 equals to 0. So really, this is the quadratic equation, and then the general form of quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 45a plus 300, the variable that we are looking for is a. Therefore, x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 35. And finally, the coefficient c equals to 300. So we have all the data in order to find out the value of a, the variable that we are looking for in this quadratic equation. We just have to put the data inside the general formula for x, and in this way we will find out the value of a, the value of the values of a, because x equals to a. We will do it now, and again x equals to a, so we substitute x by a. And it is equals to minus b. b is minus 45, therefore minus b is minus 45, that is plus 35, plus minus, you have the square root of b squared. b is minus 45, therefore b squared is minus 45 squared, that is 1225, minus 4 times a times c. A is 1, therefore minus 4 times a is minus 4 times 1, that is minus 4, times c, c is 300, so minus 4 times 300 is minus 1200. So in total, minus 4 times ac equals to minus 1200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we actually found out that a, that is the variable that we are looking for in this quadratic equation, equals to 335 plus minus square root of 1225 minus 1200 over 2. So a equals to 35 plus minus 1225 minus 1200 is 25. So inside root we left only with 25 over 2. So a equals to 35 plus minus, the square root of 25 is 5 over 2. So a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20. The second solution for a is that a equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for a is that a equals to 15. And again, we have two solutions for a equals to either 20 or 15. Okay, so in the next step, we will do a construction. First of all, this is the red triangle AQP. This red triangle AQP, side AQ plus to side AP, therefore triangle AQP is an isosceles triangle. QP is of course the base of the isosceles triangle, triangle AQP. Again, QP is the base of the isosceles triangle, triangle AQP. So, in the next step, we do a construction that is to say from the vertex A, from triangle AQP, the isosceles triangle, triangle AQP, we will go perpendicular to the base QP. Again, from A, we will go perpendicular to the base QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in the base QP. This point is point Z. So in conclusion, actually have the associated triangle AQP. For the vertex A, we go perpendicular to the base QP. So here we can implement rule 21 on the associated triangle, triangle AQP. So, repeat clicker on rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. So this is triangle ABC, this is an associated triangle where cos side AB equals to side AC. From the vertex A, BC is of course the base of the associated triangle, triangle ABC. For the vertex A, we go perpendicular AO to the base BC. Again, from the vertex A, we go perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 21, the perpendicular to the base BC bisects the base BC. If it bisects BC, it means that each half must be equal to BC over 2, of course. So the first half BO equals to BC over 2. The second half of BC is OC, that also equals to BC over 2. So in total, BO equals to OC equals to BC over 2. So can we implement rule 21 in our drawing? In our drawing, we have the perpendicular AZ to the base QZ bisect the perpendicular AZ to the base QP bisect the base QP. So each half must be equal to QP over 2, of course. The first half OZ is equals to QP over 2. The second half of QP is also equals to QP over 2. So write it down. We found out that in the associated triangle, triangle AQP, according to rule 21, of course, the first half QP is of course equals to the second half ZP. QZ, the first half equals to the second half ZP. And each half, of course, equals to QP over 2, because QP is in bisected. repeat again, according to Rule 21, this isosceles triangle, triangle EQP, the perpendicular AZ bisect the base QP. So each half must be equal to QP over 2. The first half, of course, equals to the first half QZ equals to the second half ZP, and each half must be equal to QP over 2 because QP is bisected. So this is the implementation of Rule 21 in our drawing. This equation. QP is 24, therefore QP over 2 is 24 over 2. QP is 24 over 2, 24 over 2 is 12. And from this equation, QP equals to QZ equals to QP over 2 equals to 24 over 2 equals to 12. We graph that QZ equals to ZP equals to 12. QZ equals to ZP equals to 12. QZ equals to 12. The second half ZP also equals to 12. Those two angles now defined as vertex angles. You know that vertex angles are equal to each other. Those two vertex angles are equal to each other. So if we define the size of this vertex angle as alpha, then the size of this vertex angle must also equal to alpha. So in the right green triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in a triangle. Likewise, in this green right triangle QSB, this angle equals to alpha. What about this angle? Actually, SM is a tangent to the circle at point M. SM is a tangent, it is absolutely a straight line. SM is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of SM at point B? We have this angle that is the right angle, plus this missing angle. Total the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size, according to Rule 3, of course. So I told them we should find out that the green triangle QSB is the right triangle. So in the right green triangle QSB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see that those two green triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we will find out that all the angles of this green right triangle SQB are corresponding equal to all those angles of this green right triangle AQZ, and therefore those two right green triangles are similar to each other according to angle similarity rule. So I write it down. This is the green right triangle QBS. and similar, it is similar to this right triangle AZQ. According to angle similarity rule. Again, I should found out that the right green triangle QBS is similar. This is the sign of similar to the right green triangle AZQ according to angle similarity rule. And for the fact that those two right green triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side QS of this green right triangle QSB, or side AQ of this green right triangle AQZ, is equal to side QB of this green right triangle SQB, or side QZ of this green right triangle AZQ. Repeat again, from the fact that those two right green triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side QS of the right green triangle QSB, or side AQ of the right green triangle AZQ equals to side QB of the right triangle QBS, or side ZQ of the right green triangle AZQ. QS is 25. Over AQ is X, that is the variable that you are looking for in this question. And it is equal to QB. QB equals to A. Over QZ. QZ equals to 12 units in its length. So in total, we actually found out that 25 over X equals to A over 12. Again, 25 over X equals to A over 12. So here we will cross multiply this equation. And finally we get that A times X equals to 25 times 12 is 300. So A times X equals to 300. Here we will divide this equation by A, and finally we get that X, that is the variable that we are looking for in this equation, is equal to 300 over A. Actually, we already found out that A equals to either 15 or 20. We just have to substitute A by 15 or 20, and this way we get the value of X, that is the variable that we are looking for in this question. But the problem is, what is the real value of A? Is it 20 or 15? In order to find out what is the real value of A, I will draw this right triangle ABC with the circle that is inscribed inside it, and this right triangle with the circle in order to find out what is the real value of A. Is it 20 or 15? And then we just have to substitute A by 20 or 15, and this way we get the value that we are looking for this equation, that is X. So I copied this right triangle with the circle that is inside it, In this is the new drawing of the right triangle with the circle that is inscribed by triangle ABC. And we already found out that QB equals to AQ equals to X. We define the point of tendency BC with this circle. This point is point M. We define the center of this circle. This point is point O. We define the radius of this circle as R. In the next step, we will join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, OM is the radius of the circle. This is equals to 1 according to our definition. The radius OM that is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1, of course. Likewise, point Q is the point of tendency of tangent AB with this circle. So in the next step, we will join points O and Q together by a straight line. OQ is of course the radius of this circle. Is equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So, in the small quadrilateral QOMB, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Quadrilateral QOBM has 4 rectangles, therefore we can write quadrilateral QOMB as a rectangle, although it is a square, we can relate to it as a rectangle. Okay, because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in this small rectangle QOMB, side OM equals to the opposite side QB, but OM is R, therefore the opposite side QB must be also equal to R units in its length. QB equals to A and A equals to R. In the next step, we will do another construction, that is to say, we will extend the radius MO, that is equals to R, we will extend the radius MO by a straight line until it touches the circle. We define the touching point of the extended radius OM with this circle, this point is point Z. OM is the radius, it is absolutely a straight line. We will extend the radius OM, and it is a straight line by straight line. The result MZ must be also a straight line. MZ is a straight line, so if we focus on the right side of the straight line MZ at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have on the right side of the straight line ZM at point O? We have this angle, this right angle, plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction. That is to say, from AB, we will go tangent to the circle that will be tangent at point Z. Again, from AB, we draw a tangent to the circle that will be tangent to it at point Z. It's definitely possible to do it. You can choose the right point that if we draw the tangent, it will be tangent to the circle at point Z. And define the touching point of the tangent with AB, this point is point T. So TZ is the tangent to the circle at point Z. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle is equals to R. The radius OZ is equals to R, the radius OZ is drawn to point Z, that is the point of tendency of tangent TZ with this circle. And whenever you overdo such is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that according to run, this must be equal to 90 degrees in its size. So in this small quadrilateral TZOQ, we have 1, 2, 3 triangles, and therefore this fourth triangle must be equal to 90 degrees in its size. So in quadrilateral, the upper quadrilateral TZOQ, we have 4 triangles, therefore we can relate to quadrilateral TZOQ as a rectangle, although it is actually a square. So quadrilateral TZOQ is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle TZOQ, side ZO must be equal to the opposite side TQ. But ZO is out, is the radius of the circle, therefore TQ must be also equal to R units in its length. So here we have QB equals to R and R equals to A. Or A equals to R equals to QB. So you can write down that A equals to QB equals to R. Again, A equals to QB and QB equals to R. A equals to QB and QB also equals to R. Or in other words, QB equals to simultaneously to A and R. Okay. What about line segment AQ? AQ equals to X. This is the variable that we are looking for. So we can write here that AQ equals to X from one side, but from the other side, AQ consists of 2 line segments, AT plus CQ. Again, AQ in total equals to AT plus CQ. But TQ is R, therefore AQ in total equals to AT plus R. Again, AQ in total equals to AT plus R. Or R plus AT, doesn't matter. It is AT plus R. Again, AQ equals to AT plus R. So here we have AT plus R is definitely greater than R because AT is a positive number. AT is a line segment. The line segment must be a positive number. Therefore, AT plus R must be greater than R. So you can write here that AT plus R is greater than R. And from this long equation, from this long inequality, equals to q, b equals to r, less than at plus r equals to aq equals to x, we get that a is smaller than x. A is smaller than x. Or x is greater than a. And x is greater than a. Actually, the fact that x is greater than a will help us to verify what is the real value of a, whether it is 15 or 20. So just right now found out that x is greater than a, and we have two solutions that are possible for a. According to the solution of the quadratic equation, a could be 20 or a could be 15. We already found out that x equals to 300 over a. So can I do that x equals to 300 over a. So if a equals to 15, it means that x equals to 300 over 15, that is 20. Then again, if a equals to 15, then x equals to 20. Likewise, if a equals to 20, it means that x must be equal to 300 over 20, that is 15. Then again, if a equals to 20, then x must be equal to 15. So we have x is equals to 15 is less than 20. 15 is definitely less than 50. And 15 is less than 20. And 15 is less than 20. But 20 equals to a. So we can write here that 20 equals to a. And from this inequality, we derive that x is less than a. Okay, x is less than a. But it contradicts our findings that x must be greater than a. If x is greater than a, x cannot be less than a. So due to this contradiction, we can send the solution. A cannot be equal to 20. This is the fourth solution, and we have to only the only other solution that a equals to 15. Now check if a equals to 15. The solution here, x equals to 20. 20 is definitely greater than 15. But 15 equals to a, so we can write that 15 equals to a. And for this inequality, x equals to 20 greater than 15 equals to a, we derive that x is greater than a. X is greater than a, exactly like our findings that x must be greater than a, x must be greater than a. Therefore, the other solution is the correct solution. That is to say, the variable that we are looking for this equation, x is equals to AP is equal to 20 units in its length. So again, I have found out that Remember that you're looking for this question. The length of this line segment AP is equals to x is equal to 20 units in its length. Okay, this is the solution to the second question. So in the next step, our sum of the lecture, we'll start with the first question, of course. Our task in the first question is to find out the radius of this circle that blocks quadrangle ABCD, or quadrangle ABCD is inscribed by this circle. In addition, you know that chord AC is the diameter of this circle. Side AB of quadrangle ABCD equals to side BC. We also know that the perimeter of this quadrangle ABCD equals to 18 units in its length. That is to say, the sum of its side lengths, in total it is 18 units. AB plus BC plus CD plus DA equals to 18 units in total. We also know that the area of this quadrangle ABCD is equal to 16 square units. Again, our task is to find out the radius of this circle. So, in the first step, we define the side lengths of quadrangle ABCD with letters. We define the length of side AB as A, therefore side BC must be also equal to A because they are equal to each other, AB equals to BC. Likewise, we define the length of side AD as B, and we define the length of side D as C. In the next step, we implemented Rule 7 in our drawing. So please click on Rule 7. According to Rule 7, if a peripheral angle is subset of the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB. That subset of chord AB, that is the diameter of the circle, therefore must be equal to 90 degrees in its size. So according to Rule 7, if a peripheral angle that subset of the diameter of the circle must be equal to 90 degrees in its size. So we can implement Rule 7 in our drawing. In our drawing, we have peripheral angle ABC, that subset on chord AC, that is the diameter of the circle, therefore must be equal to 90 degrees in its size according to Rule 7. Likewise, this is peripheral angle ADC, that subset on AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size. In the next step, we implement the Pythagorean on those two right triangles ABC and ADC. According to the Pythagorean theorem, in any right triangle, the square of their corners equals to the sum of the squares of the perpendiculars. So, in this right triangle ABC, It means that AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, the right angle ABC according to the Pythagoras theorem. AC squared equals to AB squared plus BC squared. The hypotenuse AC is the missing side, so it is, and it equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, we found out that AC squared equals to A squared plus A squared, that is 2A squared. AC squared equals to 2A squared according to equation 1. In the next step, we implemented the Pythagoras theorem on this right triangle, find ADC. According to the Pythagoras theorem, in this right triangle ADC, AC squared, that is the square of the hypotenuse, equals to 3D squared, equals to 3D squared plus DA squared. But again, the right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. AC is the missing side, so leave it as it is. And it equals to CD squared. CD is C, therefore CD squared is C squared plus DA squared. DA is B, therefore DA squared is B squared. So total AC squared equals to C squared plus B squared. AC squared equals to B squared plus C squared. So we have two different equations for AC squared. According to equation 1, AC squared equals to 2A squared, while according to equation 2, AC squared equals to B squared plus C squared. So in the next step, we get an equation 3 that says that AC squared according to equation 1 must be equal to AC squared according to equation 2. And according to equation 3, AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1, AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2, it equals to B squared plus C squared. So in total, according to equation 3, 2A squared equals to B squared plus C squared. Here we divided this equation 3 by 2, and we found out that B squared plus C squared over 2 equals to A squared. This is according to equation 3. It is given us the equation that the perimeter of this polynomial ABCD equals to 18. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is A, CD is C, and DA is B. So AB plus BC is A plus A, that is 2A, plus CD, that is C, plus DA, that is B. So total 2A plus B plus C equals to 18. Again, according to equation 4, 2A plus B plus C equals to 18. Likewise, it is given as the equation that the area of this polynomial ABCD equals to 16 square units in its size. Polynomial ABCD consists of those two right triangles, and therefore the area of polynomial ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of this right triangle ABC, plus the area of the second shape, that is the area of this right triangle ADC. The area of polynomial ABCD in total must be equal to the area of the first shape that it consists of, that is the area of the right triangle ABC, plus the area of the second shape that it consists of, the area of the right triangle ADC. It is given as the equation that the area of polynomial ABCD equals to 16, so substitute the area of polynomial ABCD by 16, and it equals to the area of the right triangle ABC. What is the area of this right triangle ABC? Is equal to the base AB times the height BC over 2. AB is A, BC is also A over 2. So in total, it is A times A over 2, A square over 2. Total area of the right triangle ABC equals to A square over 2. Area of the right triangle ABC equals to A square over 2 plus the area of the right triangle ADC. The area of this right triangle ADC in total equals to the base CD times the height DA over 2. CD is C, DA is B over 2. So in total it is C times B over 2. Total the area of the right triangle ADC equals to B times C over 2. So in total, according to equation 5, we have found out that 16 equals to A square over 2 plus B square over 2. So here we multiply this equation 5 by 2, and we found out that 16 times 2 is 32, A square over 2 is A square, BC over 2 is BC. So in total, 32 equals to A square plus BC. So according to equation 5, in total, we found out that 32 equals to A square plus BC. According to question 3, we already found out that a square equals to b squared plus c squared over 2. So we can substitute a squared in this equation 5 by b squared plus c squared over 2 from this equation 3. We did it, and we found out that 32 equals to a squared, that is b squared plus c squared over 2 plus bc. So total, according to equation 5, we found out that 32 equals to b squared plus c squared over 2 plus bc. So 32 equals to b squared plus c squared. Here we multiplied bc by 2 and then we divided by 2 in order to overcome the factor of this expression. So it is 2 times bc over 2. So we change nothing. Multiplied by 2 and then we divided by 2, therefore we change nothing. So in total, we found out that 32 equals to b squared plus c squared plus 2 times b times c over 2. So here we multiplied this equation 5 by 2, and we found out that 32 times 2 is 64 equals to b squared plus c squared plus 2 times b times c. So here we use the algebraic identity that says that a squared plus b squared plus 2 times a times b equals to a plus b squared. According to this algebraic identity, b squared plus c squared plus 2 times b times c equals to b plus c squared, and it equals to 64. So in total, according to equation 5, 64 equals to b plus c squared. So here we took a root out of this equation and we found out that the square root of 64 is 8, and the square root of b plus c squared is b plus c. So in total, according to equation 5, we found out that b plus c equals to 8. This is according to equation 5. But according to equation 4, we already found out that 2a plus b plus c equals to 18. Therefore, we can substitute b plus c in this equation 4 by 8 from this equation 5. We did it, and we found out that 2a plus b plus c, that is 8, equals to 18. Here we subtracted 8 from this equation 5, and finally found out that 2 equals to 18 minus 8 is 10. So 2 equals to 10. Here we divided this equation 4 by 2, and finally found out that a equals to 10 over 2, that is 5. A equals to 5 minutes in its length. So actually, this is side BC, this is equals to A, and A equals to 5, therefore BC equals to 5. Here AB equals to A, and A equals to 5, therefore AB equals to 5. So in the next step, we implemented the Pythagoras theorem on this right triangle ABC. So according to the Pythagoras theorem, in this triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. But again, the right triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. So AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total, we found out that AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. We substitute 50 by 25 times 2, and we found out that AC squared equals to 25 times 2. Here we took out of this equation, and we found out that AC equals to the square root of 25, that is 5, so inside those we left only with 2. So in total, we found out that AC equals to 5 times square root of 2 units in its turn. AC is the hypotenuse of triangle ABC. AC is also the diameter of the circle, according to what is given as the equation. We know that the radius of any circle equals to the diameter over 2. So the radius R, define the radius of R, the radius R of our circle must be equal to the diameter AC over 2. The diameter AC equals to 5 times square root of 2, so we divide the diameter AC by 2 and get the radius R. So R equals to the diameter, that is 5 times square root of 2 divided by 2. So the radius of this circle, that is the radius that we are looking for in this equation, it is equals to either 5 times square root of 2 over 2 units in itself, or in terms of numbers, the radius of this circle equals to 3.536 units in itself. So we need to repeat on the first question. In the next step, I repeat on the second question. In the second question, our task was to find out the length of this line 7 AP that equals to x. We have to find out the value of x. So in the drawing, we have a circle that is inscribed by the triangle ABC. This is a tangent SM, that is tangent to this circle point M. This is angle ABC, this is right angle. This is line 7 SQ. This is equals to 25 units in its length. This is called QP. This is equals to 24 units in its length. Again, our test to find out the length of this line 7 AP. This is equals to x. We have to find out the value of x. So first of all, we implemented in our drawing rule 2. So please click on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle. This is the common external point, point P. On this common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. This is to say the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So you can actually implement rule 2 in our drawing. One to another drawing. If you focus on this common external point, point A, for this common external point, point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say AP equals to AQ, but AP equals to x. Therefore AQ must be also equal to x. We define the length of tangent BM as A, and focus on this common external point, point B. For this common external point, point B, we have two tangents to this circle, tangent BM and tangent BQ. According to rule 2, they are equal to each other. That is to say BM equals to BQ, but BM is A, therefore BQ must be also equal to A units in its length. So in the next step, we focus on this common external point, point S. For this common external point, point S, we have tangent SM, that is tangent to this circle at point M. Likewise, we have here chord PQ of this circle, chord PQ, the extended chord PQ touches point S. Again, the extended chord PQ touches point S, So all the requirements for rule 10 are satisfied, and therefore we can implement rule 10. And please click on rule 10. According to rule 10, rule 10 is true in any circle, so if AB is any chord, in the circle, and PT is a tangent to the circle, then the following equation is true that PT square equals to PT square equals to PA times PB. Again, PT square equals to PA times PB. So in the drawing, we have a circle. This is the common external point, point P. For this common external point P, we have tangent PT. The tangent of the circle is point T. Likewise, we have here chord BA, and the extended chord BA touches point P. So in this drawing, the following equation is true that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we actually implement rule 10 in our drawing. So in the version before, all the requirements of rule 10 are satisfied, right? From the common external point S, we have tangent SM, that is tangent to this second point M. Likewise, we have here chord PQ, the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true that SM square equals to SQ times SP. Again, SM square equals to SQ times SP. And again, if you focus on the common external point S, according to rule 10, SM square equals to SQ times SP. SQ is 25. SP in total equals to SQ, that is 25, plus QP, that is 24. 25 plus 24 is 49. Then again, SM square equals to SQ, that is 25, times SP, that is 45. So we should know that SM square equals to 25 times 49. Here we took out all the equation, and we found out that SM equals to the square root of 25 is 5. And the square root of 49 is 7. So SM equals to 5 times 7, that is 45. This is tangent SM is equals to 35 units in its length. What is the length of this line segment SB? SB equals to SM minus BM. SB equals to SM minus BM. So SB equals to SM, that is 35, minus BM, that is 8. So total SB equals to 35 minus units in its length. So in the next step, implement the Pythagoras theorem on this item SQB. So in this item SQB, according to the Pythagoras theorem, SQ square equals to QB square plus BA square. Now I get SQB according to the Pythagoras theorem, SQ Q square, that is the square of the hypotenuse, equals to QB square plus BA square. QS equals to 25, therefore QS square is 25 square. That is 625. And it is equals to QB square. QB is 8, therefore QB square is 8 square. Plus SB square. SB is 35 minus 8, therefore SB square is 35 minus 8 square. So in total, if I know that $625 equals to 8 square plus 35 minus 8 square. So 625 equals to 8 square. We open the brackets of this expression. 35 minus 8 square equals to 35 square, that is 1225, plus 8 square, minus 2 times 35 times 8, that is 178. So 625 equals to 8 square plus 8 square is 2 8 square. And we have plus 1225, 178. Here we subtract 625 from this equation, so this side of the equation we have nothing, that is to say 0. While on the other side of the equation we have 2a squared, 178, and 1225 from 625 is 600. So in total, if you found out that 0 equals to 2a squared, 178 plus 600. Here we divided the equation by 2 and find out actually that 2a squared over 2 is a squared, 178 over 2 is 145a, plus 600 over 2, 600 over 2 is 400. 0 over 2 is 0. So in total, a squared minus 45a plus 300 equals to 0. And again, if you found out that a squared minus 45a plus 300 equals to 0. So this is the quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 45a plus 300 equals to 0, the variable that we are looking for is of course a, so x equals to a. The coefficient a equals to 1, the coefficient b equals to 145, and the coefficient c equals to 300. So we have all the data that is needed for our specific quadratic equation in order to find out the variable that we are looking for, that is a. You just have to put the data in this general formula for x, and this way we get the value of a, because x equals to a. We did it, and we found out x equals to a, so we substitute x by a, and it's equals to, this is equals to minus b. B is minus 45, therefore minus b is minus 45, that is plus 25, plus 45, plus minus square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225, minus 4 times a times c. So it is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. C is 300, so minus 4 times 300 is minus 1200. So inside out the total minus 4 AC equals to minus 1200. So inside the out we have 1225 minus 1200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So a equals to 35 plus minus 1225 minus 1200 is 25, so inside over left only 25 over 2. So a equals to 35 plus minus the square root of 25 is 5 over 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 40 and 40 over 2 is 20. So the first solution for A is that A equals to 20. Well, the second solution for A is that A equals to 35 minus 5 over 2. 35 minus 5 is 30 and 30 over 2 is 15. So the second solution for A is A equals to 15. The first solution for A is that A equals to 20. So in the next step, we did a construction. This is to say, first of all, the green triangle AQP is an associated triangle because side AQ equals to side AP, and QP is of course the base of the associated triangle AQP. From the vertex A, we go perpendicular AZ to the base QP. Again, from the vertex A, we go perpendicular AZ to the base QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So here we can implement all 21. All 21, according to all 21, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have associated triangle, triangle ABC. Triangle ABC is an associated triangle because AB, side AB equals to side AC. For the vertex A, BC is of course the base of triangle ABC, the associated triangle ABC. From A, we go perpendicular AO to the base BC. Again, from point A, we go perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this all 21, the perpendicular AO also bisect the base BC. Again, the perpendicular AO to the base BC bisect the base BC. That is to say, divide the base BC into two halves. Each half must be, of course, equals to BC over 2. So the first half equals to the second half. That is to say, BO equals to OC, and each half equals to BC over 2. So BO equals to OC equals to BC over 2. So we can implement all 21 in our drawing. Well, for our drawing, we have the perpendicular AZ that bisect the base QP. So the first half QZ must be equal to the second half ZP, and each half must be equal to QP over 2. So OZ equals to ZP equals to QP over 2. The associated triangle in QP according to all 21. The first half of QP, that is QZ, equals to the second half ZP. Each half must be, of course, equals to QP over 2. QP is 24, so 24 over 2 is 12. From this equation, we know that QZ equals to ZP equals to 12. This first half ZP equals to 12, and the second half QP also equals to 12. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this vertex angle is alpha, then the size of this vertex angle must be also equal to alpha. So in this green triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this part of this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, this green triangle SQB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Those two right angles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the angles of this right triangle QSB are corresponding equal to all the angles of this green right triangle AQZ, and therefore those two right angles are similar to each other according to angle similarity rule. And again, if you found out that the right green triangle QBS is similar. This is the side similar to that ZQ according to again similar report. And for the fact that those two right rectangles are similar to each other, we realize that the following relationship exists between their sides. We realize that side QS of the right rectangle QSB or side EQ of the right this right rectangle AQZ equals to side QB of this right rectangle SQB or side QZ of this rectangle AQZ. With again from the fact that those two rectangles are similar to each other, we realize that the following relationship exists between their sides. We realize that side SQ of the right triangle SQB or side AZ of the right triangle AZQ equals to side QB of the right triangle QBS or side ZQ of the right triangle AZQ. QS is 25, AQ is X, QB is A, and QZ is 12. In total, if we want to know that 12 over X equals to A over 12, 25 over X equals to A over 12. Here, of course, multiply this equation, and find that A times X equals to 25 times 12, that is 300. So in total, A times X equals to 300. Here we divide this equation by A, and find that X equals to 300 over A. Now we have to find out what is the real value of A. Is it 20 or 15? In order to find out what is the real value of A, I copy this triangle ABC, the circle that is inscribed inside it, inside the new drawing, and analyze the drawing in order to find out what is the real value for A. Is it 20 or 15? So here, this is the right triangle ABC, this is the point from the original drawing. If it's circled, that is inscribed inside it. We only found out that QB equals to A, AQ equals to X. We find the point of tendency of the ABC with this circle as M. We find the radius of this circle as O. We define the center of this circle as O. We define the radius of this circle as R. We join points O and M together by straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to R. The radius of M that is equal to R, the radius of M is drawn to point M, that is the point of tendency of tangent BC with this circle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Point Q is the point of tendency of tangent AB with this circle. So we join points O and Q together by straight line. OQ is the radius of the circle that equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the slope on the other OQBM, we have 1, 2 rectangles, and therefore this fourth piece area must be equal to 90 degrees in size according to the rule that says that the sum of the areas area for the other is equal to 360 degrees. So for the other OQBM is 4 rectangles, and therefore it is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle QOMB, side OM must be equal to the opposite side QB. But OM is R, therefore the opposite side QB must also equal to R and C itself. So in total QB equals to A equals to R. The next step we did the construction, that is to say, we extended the radius MO by straight line until it touches the circle. We define the touching point of the extended radius MO with this circle, this point is point Z. The radius MO is absolutely straight line. We extend the straight line by straight line. The result MZ must be also a straight line. So if we focus on the right side of the straight line MZ at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles for one side of the straight line is equal to 180 degrees. So which angles we have the right side of ZM at point O? We have this angle that is right angle, plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So we have here point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle that is equal to R. In the next step we did another construction, that is to say from A and B, you do a tangent to the circle at point Z. Again, from AB, we do a tangent to the circle at point Z. We constructed the tangent in such a way that it will be tangent to the circle at point Z. So TZ is a tangent to the circle at point Z. The radius OZ is equals to R. The radius OZ is drawn to point Z, that is the point of tendency of tangent TZ in this circle. And now, what is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to all 1. So in total, in the upper quadrant of TZ or Q, we have 1, 2, 3 articles. This angle equals to 90 degrees according to all 3. So we have 1, 2, 3 articles, and therefore this 4 pieces must be equal to 90 degrees in its size. So in size quadrant TZ or Q, we have 4 articles, and therefore it is a rectangle. And we know that the opposite sides of rectangle are equal to each other. So in the small rectangle TZ or Q, side ZO must be equal to the opposite side TQ. But ZO is out, therefore the opposite side TQ must be equal to 1 in its line. So we only found out that A equals to QB, and QB also equals to R. So QB, constant QB from one side is equals to R, but from the other side QB from one side is equals to A, but from the other side is also equals to R. Therefore A equals to QB equals to R. Likewise, what about line segment AQ? AQ from one side equals to X. Again, AQ equals to X. AQ equals to X from one side, but from the other side, AQ also equals to AT plus CQ. So AQ in total equals to AT plus CQ, but CQ is also in total AQ equals to AT plus R. Again, from the other side, AQ equals to AT plus R. From the other side, AQ equals to AT plus R. AT is a positive number, it is a side. This is the side length, the length of side AT, it is a length, so it must be a positive number. Therefore, AT plus R it is absolutely greater than R, because AT is a positive number. So we can write it that AT plus R is greater than R. And from this zoning equality, we get that A is smaller than X. Again, A is smaller than X, so X is greater than A. So we can write here that X is greater than A. We have two solutions that are possible for A. A either equals to 20 or can be equal also to 15. So which is the right solution? We found out that X equals to 300 over A. So can I idea that X equals to 300 over A. So if A equals to 15, then X equals to 300 over 15. This is 20. Then X equals to 20. So if A equals to 15, then X must be equal to 20. Likewise, we have A equals to 20, therefore X equals to 300 over 20, that is 15. So if A equals to 20, then X must be equal to 15. So X equals to 15, 15 is definitely less than 20, but 20 equals to A. I tell that 20 equals to A, and from this equation, from this inequality, we grab that X is less than A, or A is greater than A, or A is greater than X. Here A is greater than X, but here we have A is less than X. Here we have A is greater than X, and here we have A is less than X. So due to this conservation, we tested the solution, A cannot be equal to 20, and we left only with the other solution that is possible, that A equals to 15. And then X equals to 20. X equals to 20. 20 is definitely greater than 15. But 15 equals to A, so we can write that 15 equals to A. And from this inequality, X equals to 20 is greater than 15 equals to A. We will derive that X is greater than A. X is greater than A, exactly what, like we already found out, that X must be greater than A. so there is no contradiction to other findings, and therefore it is the real solution. A equals to 15, and then x must be equal to 20. So x is equals to AP is equal to 20 units in itself. Actually, this is line segment AP is equals to x, and x equals to 20 units in itself. Okay, thank you very much.